let's start this up. So I have not finished marking your tests. I'm sorry, I tried. I didn't finish. But as soon as they're marked, I'll bring your tests. So I'll probably mark them on the plane tonight, and then as soon as they're marked, though, I'll post your grades on Moodle, and then you'll get them back the following class. So you will get them back. Like I said, I do have 3 blank tests from people who didn't show up. So if you want one to practice with, there's 3 here. Yeah, I'll post the solutions on Moodle. But yeah, that's it about the tests. What else? I feel like there might have been something else. But anyways, so today we're starting chapter 4? Yeah, chapter 4. So what's nice is test 1 is done. Test 1 is weird, and I like when it's over because it's all this like weird stuff going on. It's like, oh, here's a little bit of this and a little bit of that and a little bit of this. And so now in part 2 of the textbook, we really settle down, and now we start to talk about simple interest, and then that's going to build into compound interest, and then we build into annuities. And we basically just keep talking about the same thing over and over and over again from this point on. Right. Today, we're basically just going to review exponents and log rules, right? How do we deal with exponents? How do we deal with logs? Because we'll need them to solve equations later on. But besides that, there's nothing really fun going on today, but I don't think anyone minds if we do it a little bit quicker. No, so let's get to it. All right. So we're getting into part 3, is that right? I have part 3, but I thought it was part 2. Part 3, who knew? Part 3, which is on simple and compound interest. And we're starting in section 4.1, which is called the basics. But like I said, I feel like every first section is called the basics, so it's not very descriptive. But what we're going to talk about is exponents and logs. Exponents and logs. Okay. We'll start by talking about exponents, which you could also call powers if you wanted to. Switch this over. So if we have something like a times 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 a, what? N times, we could shorthand that as a to the power of n. Where a is the base, right? So we call a the base, and n is the power. Right? Or vice versa, or exponent. So in case that wasn't clear in words, well, sort of, a to the power of n is n a's multiplied together. As a quick example, if we've got 5 times 5 times 5 times 5, 5 is our base, right? And so we've got 5 to the power of 1, 2, 3, 4. Or if we could write out 2 to the power of 5, 2 is our base, so we've got 2. You can use the times like the x times or a dot. Usually I just do a dot. 2 times 2 times 2 times 2. 1, 2, 3, 4, 5. So these are exponents, right? Hopefully they're not too foreign, right? But there's also rules with exponents, right? How can we how can we multiply the same base and combine the exponents, for example? And so we've got rules of exponents. And if you don't know these already, you will have to work with them and memorize them to some degree, right? And so you're not doing illegal math. These rules are on page 92 of your textbook. I have here, yeah. I haven't changed my textbook, but I feel like I should show you guys where it is. So they're just in theorem 4.1 of your textbook. Okay. But we'll write them out here and kind of talk it out a little bit more than what's there. So we need to lay out the ground rules for the rules. Okay. Things like we're going to let a be greater than 0, which means, I'll do in light blue kind of my explanation, right? Which means that the base must be a non-zero, right? Because it has to be greater than 0, so it can't be equal to 0. A non-zero positive number. Well, that doesn't really say number, does it? Number. We're also going to say that m and n are in the set of real numbers. I know, gross, right? I'll explain what that means. So the little e sort of looking thing is in the set, and the capital R that's kind of fancy stylized is the set of real numbers, which is basically any number that you can think of from negative infinity to positive infinity. So it's just saying m and n can be any number that you want to deal with, right? And so here, this is saying that m and n are in the set of real numbers, right? The set of real numbers is any number, any number between negative infinity and infinity. So it's not putting any restrictions like, oh, it can't be 0 or anything like that. It's just saying m and n can be any number. Any questions about that so far? Right. So in our examples, we're going to use a, m, n. We'll also throw in a b, but it behaves the same way as a, just another base, right? And yeah. Well, they'll behave the same way. They're going to be powers. Yeah. So you'll see. The first rule is that we can write a to the power of n is the same as a times a times a, which is really just a multiplied n times, which we already established, right? A multiplied n times. So we've already got the first rule figured out, right? The second rule, the second very useful rule, is that if we have a to the power of m times a to the power of n, we can combine these because they have the same base, a. We can rewrite this as a to the power of m plus n. That's a rule. So that's where they come in. Yeah. So if multiplying powers with the same base, we can simplify by adding the exponents. Okay. Same idea, a to the power of m over a to the power of n. As long as we're dividing the same base, we can rewrite this as a to the power of m minus n. Same idea. So as long as we have the same base, right? So if dividing powers, oops, got stuck on the S, of the same base, we can simplify by subtracting the exponents. Simplify by, by subtracting the exponents. Well, fourth rule is that if we have a to the power of m to the power of n, we can rewrite that as, we can just remove those brackets and say, well, that's the same as a to the power of m times n. This one you don't really need an explanation for because it's just an extension of rule number 1, right? Instead of a as your base, imagine that you have a to the power of m as your base. A to the power of m times a to the power of m times a to the power of m. So you can rewrite that as a to the power of m times n. So this is just an extension. Oops. An extension of rule number 1. If we have a times b to the power of m, then we can expand this by bringing the power of m onto both of the bases, a and b. So we get a to the power of m times b to the power of m. if multiplying two bases the power expands inside onto both bases. Bath. Onto both bases. Any questions so far? Pretty good? Good. Then we'll do rule number 6. Same idea, a over b to the power of m. We rewrite as a to the power of m over b to the power of m, which is really just an extension of rule number 5, right? Division is a form of multiplication, right? We're just multiplying by the inverse. And so an extension of rule number 5. The 7th rule is that a to the power of 0 is 1. We already talked about anything to the power of 0 is just 1, right? So this is just a fact. Yeah. A useful thing that we might have is a to the negative n is the same as 1 over a to the power of n, right? And so we use this a lot where if we want to bring something from the denominator up to the numerator, right? So we want to bring it from the bottom to the top, then we can say, well, we can rewrite that power as a negative power up top, right? And it behaves the same way. Right, and so we can rewrite a power in the denominator and actually we end up using this quite a bit going this way from here to here, right? And so all these rules, you can go back and forth, right? But for this one especially, we actually work a lot from 1 over a to the n. We rewrite it as a to the negative n. So we can rewrite a power in the denominator as a power in the numerator by negating the power. Right? By making that power negative. Rule number 9 is that a to the 1 over n, right? So now we have 1 over n as our power, is the nth root of a. Okay? So usually if we're writing the nth root, then we put the n in the little hook. Right? Maybe I'll write it, I'll try to make it a little bit bigger. There. We're used to the square root, right, which is just the second root. Usually then we don't write anything in that hook, but we could have the 3rd root, the 4th root, the 5th root, and to calculate those on our calculator, same deal, right? If I have to take the 5th root of something, then let's say the 5th root of 2, right? Then on my calculator, I can't do that. I have to do 2 to the power of 1 over 5, right? And so we're working this way to here most often, right? Just to be able to use our calculator usually. Okay. We can rewrite the nth root as a power if needed, right? And that's kind of when we use this. And our last rule, kind of the same idea, a to the power of m over n, right? Now we have to think, okay, well, this is the same as a to the power of n, to the power of 1 over n. And this is by rule number 4. But we can keep changing that and say, well, that's the same as the nth root of a to the power of m, which is an extension of rule number 9. Just treating a to the power of m as one thing. Any questions about those rules? Good refresher, or maybe a little bit stressful if none of this is looking familiar. But either way, we'll learn them. So let's just do a little example. Say you have to simplify something like a to the power of 4 times a to the power of 8 over a to the power of 7. Bless you. There's lots of orders that we can do this, but at the end of the day, we're all going to end up doing the same thing, right? We could combine the powers up top because we have the same base overall, right? So we could combine those powers up top, or we could start by bringing a to the 7 up to the numerator, right? So we've got options. I'll just pick a lane and stick with it, but you'll see we'll end up at the same answer regardless, right? And so if I'll just rewrite the problem here so that I have a little bit of room. So we can combine the powers up top if we want, right? And so a to the power of 4 plus 8 over a to the power of 7. This is by rule number 2. Which we can rewrite as a to the power of 12 over a to the 7, right? That's just simplifying the 4 plus 8. And then I'm going to rewrite this as a to the power of 12 times a to the negative 7, right? Bringing that a to the power of 7 up to the numerator by making the power negative, right? And so this is by rule number which? 3? Oh, 8. By rule number 8. We could have skipped a step and said, well, because we have a to the 12 over a to the 7, we have the same base. So then we could have just used rule number 3, right? But we're going to end up at the same thing, right? A to the m over a to the n is a to the m minus n. But what you'll see is when you add these powers, one is going to be negative, so it is just m minus n, right? So, oops, other color. Or number 3, if you prefer. Because we get a to the 12 plus negative 7, right? Technically, we're still adding, but usually we just do 12 minus 7, right, if we get to that point. But we get 12 minus 7 is a to the power of 5. So this step was rule number 2. Oh, which one is complaining? This one. And that's it, simplified. Can't go any further. No, not explicitly, but you will need to know how to work with exponents in order to solve some of these problems. So that's why we're just reviewing how to deal with exponents, how to deal with logs, so that you can use them on the real problems. Yeah. Let's do another example. A little bit bigger this time. If I asked you to simplify 1 plus I to the power of 3 times 1 plus I to the power of 9 over 1 plus I to the power of 6. The key here is going to be to treat 1 plus I as one thing, right? Treat it as your A, right? 1 plus I is everywhere. That's the base everywhere, right? Because it might be tempting to bring in that power of 3, right? But I'll show you why you can't do that. Okay? So I'll even do it in red. It might be tempting to say that 1 plus I to the power of 3 equals 1 to the power of 3 plus I to the power of 3. But don't. Because these two things are not equal to each other, right? And so remember, by definition, 1 plus I to the power of 3 is 1 plus I times 1 plus I times 1 plus I. Right? 1 plus I times 1 plus I times 1 plus I. Right? I guess my little warning doesn't make sense if I have the not equal to. Because then it's true. Not a warning at all. Okay, right? So we've got our base to the power of 3. It's just the base times the base times the base. And so, oh, hello? Yeah. I think I hit something. We'll start expanding this, right? I do one set of brackets and then another set of brackets, right? We've talked about expanding. And so we've got 1 times 1 is 1. 1 times I is I times 1 is I, plus I times I is I squared, right? I times I is I to the power of 2. Times 1 plus I. So now I can simplify the first set of brackets to be 1 plus 2i plus I squared times 1 plus I, but I still have to expand into that second set of brackets, right? And so now I've got, remember we're foiling, so 1 times 1 oh, I guess I don't need brackets anymore, is 1. 1 times I is I. Moving on to 2I times 1 is 2I. Plus 2I times I is 2I squared. Moving on to I squared, we get I squared times 1 is I squared, plus I squared times I is I to the power of 3. Oy. Simplifying, collecting like terms, we get 1 plus 3I plus 3I squared plus I to the power of 3. Right. And so now it's obvious that that is not the same as 1 to the power of 3 plus I to the power of 3, right? So I don't want to see if you're adding or subtracting inside, right? You can't just bring in that power because they're not going to be the same thing, right? So you have to be really, really careful. If you're multiplying, then the rules say that yes, you can bring in that power, but if you're adding or subtracting, it's a no-go, right?
We can do it simply like 3 plus 9.
Which one are you talking about? This one here? Or there? This one here? Well, I'm just showing that this is not this, right? And so that's why we can't do that, right? And so here, I'll just say that this shows that 1 plus I to the power of 3 is not equal to 1 to the power of 3 plus I to the power of 3, right? Because they're not the same. Okay. Therefore, we can only, I call it pull in the power, right? Or expand the power inside the brackets. So we can only pull in the power if we are multiplying or dividing inside the brackets, right? If we are multiplying or dividing inside the brackets, right? Not if we are adding or subtracting. To get back to the problem, right? If we have to simplify, so that was kind of a side thing because I see that a lot where people pull in the powers if you're adding or subtracting inside, and I don't want to see that. So simplify, remember this was the question, 1 plus I to the power of 3 times 1 plus I to the power of 9 over 1 plus I to the power of 6. We can easily simplify if we treat, looks, or it sounds way more fun in there than in here. They're like watching a show. Just send them home already. We can easily simplify if we treat 1 plus I as the base. Right, so treating 1 plus I as one thing, then you don't have to worry about expanding, and we're able to just treat that as the base, and we've got some powers to deal with. Right? But I know that's hard to see right away. Right? So we've got 1 plus I to the power of 3 times 1 plus I to the power of 9 over 1 plus I to the power of 6. Same idea, right? We've got some options. How about we mix things up and I'll just bring the 1 plus I to the power of 6 to the numerator this time. See what that looks like. 1 plus I to the power of 3 times 1 plus I to the power of 9 times 1 plus I to the power of 6. Negative 6. I'll clean that up actually. Which is 1 plus I to the power of 3 plus 9 plus negative 6. Which is 1 plus I to the power of 6. Nice. And this would be considered simplified because if we expand it, it actually gets bigger, right? So we would stop here. Ready for a bigger one? How about example 120? Simplify x plus 3 to the power of 5, all to the power of 3 over 2. I'll just rewrite the question over here on the left so I have some room. X plus 3 to the power of 5, all to the power of 3 over 2. I can use, I think it says rule number 4. I'm not going to scroll to it. I'm going to trust my notes. Yeah, you can ditch the brackets. Yeah, exactly. So you get x plus 3 times, or to the power of 5 times 3 over 2, right? And I'll just make a note by rule number 4. When you're doing this, you definitely don't have to tell me what rule you're using. I'm just giving it to you so that you can look back and convince yourself. So then this would simplify to x plus 3 to the power of 5 times 3. Right now we're just multiplying fractions. Multiplying fractions is easy enough, right? 5 times 3 over 2, 15 over 2. If something's to the power of 15 over 2, we're taking x plus 3 to the power of 15, and then we're taking the square root of it, right? So we can rewrite that power, the fraction in the power, as x plus 3 to the power of 5, and then technically it has a 2 in that little hook. Yes, thank you. Haha. That would have been confusing. And this is rule number 10. That lets us rewrite it like that. I'll do a little side note here that usually we write the square root as just like that, right? But for any other root, we add the number into the hook. So, but for any other root, we write the root number, I guess. Right, the third root, the fourth root, the root number in the hook. I call it the hook. for example, x to the power of 1 over 3 is the third root, which we would write as the third root of x. Same idea, x to the power of 1 over 4 is the fourth root. Fourth root of x. Why do we need to know about roots and how they behave? Well, we use roots to undo powers, right? And so we use roots to undo powers, right? So we talked about exponents, and so they're powers, right? And so now we need roots to kind of undo them. Just like subtracting undoes adding and division undoes multiplication and vice versa, right? Roots undo powers. So, for example, solve for x in x to the power of 5, or actually I'll move it to the center here. X to the power of 5 is 243. We have to do the same thing to both sides, right? So knowing that the roots undo the powers, right? If we have a power of 5, we have to take the fifth root, right? And so what we do is we take the fifth root of x to the power of 5, but whatever we do to one side, we have to do to the other side. So we have to take the fifth root of 243. Right? Taking the fifth root of something is the same as taking that something to the power of 1 over 5. Right? So we can rewrite this as x to the power of 5 to the power of 1 over 5 is 243 to the power of 1 over 5. Because the powers are multiplying, we can actually dissolve these brackets. And so this becomes x to the power of 5 times 1 over 5. We know that's going to be 1. That's how it undoes the power, right? And 243 to the power of 1 over 5 on your calculator. Oh, it sounds like you did maybe not the power of 5. I don't know what happened. It should be 3. Yeah. Here, I'll do the step by step. For 243 to the power of 1/2, you're going to put 242 on your screen. 243, oops, on your screen, and then hit the y to the x button. Y to the x is above the 9, right? It doesn't do anything, so this calculator is kind of not that good for anything but financial math later on. But 243, and then the y to the x button, and then in brackets, you'll want to make sure that you do to the power of 1 over 5 all inside brackets. Otherwise, it might just stop at 1 and then divide by 5. Maybe that's what, I don't know. So you want to do bracket and then 1 and then divided by 1 divided by 5, and then end that bracket and then equals, oh, I screwed up. Should get you to 3. So that's how you take the fifth root of 243. But also on the left-hand side, right, what's happening here is x to the power of 5 over 5 is 3. X to the power of 1 is 3, right? 5 over 5 is 1. X to the power of 1 is just x, so x equals 3. You definitely do not need to show any of this left-hand side, right? Because if you write, I want to take the fifth root of x to the 5, it's okay to just go, okay, well, once I take the fifth root of x to the power of 5, it's x. You can do that. So you can go straight from that top row down to x. That's fine. But I still want to see all this stuff. But, I mean, the 3 started here, so it's this is way more work than you need to show, right? But I just want to go through and show you why that fifth root undoes that power of 5, and this is why. Any questions about that one? Oh. All right. Example 121. Solve x times y squared is x squared minus y squared for y. We could just as easily solve for x, but let's solve for y. Right, so just like solving for anything else, what I'm going to do is I'm just going to take this whole thing and I'm going to write it in the center so that I can, or maybe off to the side so I can do a little commentary. Xy squared is x squared minus y squared. I have to move whatever I'm solving for to one side, everything else to the other side. And so I've got xy squared plus y squared, moving it to the left-hand side, is x squared. Move y's to one side. Now on the left-hand side, I've got xy squared plus y squared. I can pull out a common y squared, right? So I get y squared times x plus 1 is x squared. So pull out, I guess I should say factor. I guess that's the proper term, but whatever. The common y squared. Now I've got y squared times x plus 1. I can divide x plus 1 on both sides, and I get y squared is x squared over x plus 1. So isolate y. Technically, it's y squared. You don't need brackets around x plus 1 because it's not multiplying anything, right? And so it's not doing anything. So we could get rid of them if we want to, and I think I will in the next step. But to undo the y squared, right, we know to take the square root, right? So it's not that new, right? But I'm going to take the square root of y squared is the square root of x squared over x plus 1. One thing that's going to be important is that we have to do plus minus. Because if we're undoing the square, remember if you square a number, it becomes positive, right? So when we undo the square, right, then we've lost that negative value, which it could have been, right? And so when we take the square root, we need to consider both positive and negative values of y. Both positive and negative values of y. And this is why we add plus minus in front of the square root. So now we have y is the plus minus square root of x squared over x plus 1. Yeah. I would consider this to be simplified, but we can take it even further. Right? And so I would consider y is plus minus the square root of x squared over x plus 1 to be simplified. But we could keep going if we wanted to. If we want to. So we've got y is plus minus the square root of x squared over x plus 1. How do we keep going? We can rewrite that square root as plus minus and then big brackets x squared over x plus 1 to the 1/2. Right, the square root is to the power of 1/2. Just making sure everything's to the power of 1/2. This is rule number 9. Can bring that power inside. So we get plus minus x to the power of 2 times 1 over 2 over x plus 1, because that's all to the power of 1/2. This is rule number 6. Simplifying this, I get plus minus x over the square root of x plus 1. And you can't simplify it anymore. Any questions about that one? Okay. The graph of an exponent kind of looks like it starts off slow and then eventually it just kind of takes off, and we've got this exponential growth, right? Exponential growth, if we're talking money is good, right? Otherwise, we're talking interest, not so good if you have to pay it, that kind of thing. And so in general, an exponential graph will look like this. So we've got our x and our y coordinates here, and it'll just kind of look like, I'll draw it in a different color. Like that. This is what we call exponential growth. which just means it's slow to start, but grows faster and faster with time. But grows faster and faster with time. All right, let's get into logs. So exponents, there's rules for exponents. To undo an exponent, we have to take the root, and just kind of being familiar with those rules and applying them is a good idea. So let's just build, for example, so we know to solve for x in x to the power of 7, right, we have to take the 7th root. Right? We take, have a good weekend. Oh yeah, sorry. We take the 7th root. Oops. Oh. What if we have to solve 7 to the power of x for x? So this is where logs come in, right? Logs are the only way that we can bring down that power of x and be able to deal with it. Okay? So in come logarithms. If we need to solve for a value in the exponent, we will need to use logarithms. So if we need to solve for a value in the exponent, we will need to use logarithms. Logarithms, or just logs. So logs, you can have any base for a log, and we're not going to talk about the makeup of a log. We're only going to talk about log base e, the natural logarithm, okay? But logs can have any base. Most common bases are base 10 or base e. E is kind of like pi, right? It's an irrational number, 2.71828, da 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 da, keeps going forever. We will work exclusively in log base e. We will work exclusively in log base e which we write log and then a little subscript e. Also called the natural logarithm. The natural logarithm. And denoted by ln, right? Or usually when I write it, it just looks like a kind of a cursive ln, more of a scribble. So same that we did with the exponents, right? We're going to develop some log laws. Fun to say, fun to do. So all the log laws that we're going to develop apply to all the bases, but we're only going to be talking about log base e or ln. What's confusing is when I say log, I mean the natural logarithm. Could be any log, but for me, I mean the natural log. So all of the log laws we develop here apply to any base even though we will only show ln, the natural log. So here we go. The properties / rules of logs. And in case you're wondering, it's on page 96. If you have to go, oops, 96. If you have to go back. So same deal, we have to establish some ground rules. For here, the only things that we have to talk about are that A and B are also in the set of positive real numbers, which is just saying A and B must be positive. But they can be any number from 0. Can it be 0? Potentially exclusive of 0 up to infinity. Didn't specify, so. All right, rule number 1, and this is the most useful rule that we'll have, is that the log of a to the power of b, if we take the log of a to the power of b, it becomes b times the log of a, right? And so that's how we're going to bring this power downstairs. If we've got a to the power of b and we take the log, then we can rewrite it as b times the log of a, right? So that's why we need the logs in order to bring those powers down. The second rule is very similar, right? But if you have the log of a to the negative b, the negative b goes out in front, so you get negative b times the log of a. That's not that weird, right? But remember, a to the negative b is 1 over a to the power of b, right? So you might have to change the fraction to get there, right? And then you can take the log. The third rule says that the log of a times b is the log of a plus the log of b. Yeah. Don't worry. There's not that much longer. I promise. You guys deserve a prize for staying before a long weekend. Hey, there's still tomorrow. But, the fourth rule is that the log of a over b is the log of a minus the log of b. Okay. All right. That's it for the log rules, the log laws. Let's do an example. Let's try, if you have to solve the future value, or actually I'm going to use the notation that's on your formula sheet. We haven't used this formula, but the formula that I'm about to use, oh, never mind, it is this, is the future value is the present value times 1 plus I to the power of n. Okay. Solve this for n. We don't need to know what these things are, but future value and present value, we're using two variables for one thing. It's not very good or clean, but as long as we know what they are, then we can treat them as one thing, right? And so we've got the future value is the present value times 1 plus I to the power of n. If I want to solve for n, right, the first thing I have to do is divide both sides by the present value, just so I can get 1 plus I to the power of n on its own, right? Then I can take the log of it to bring that power down. And so I have to do the future value over the present value is 1 plus I to the power of n. Now I can take the log of both sides. So I get the log of the future value over the present value is n times the log of 1 plus I. Oops. Now I can solve for n, right? Because if I do my switcheroo, I like to have my n on my left-hand side. But really what I would be doing is I'm taking the log of 1 plus I and dividing it on both sides. So I have the log of the future value over the present value, then divided by the log of 1 plus I. And if you have your formula sheet handy, that is the formula for n, right? So that's why we need to know it, because, and even later on here on the back side of the formula sheet, right, we need to be able to solve for all the variables. Okay. What if we actually have numbers? So for example, if we have 5 equals 4 to the power of x, and we want to solve for x, rewriting it, we get 5 is 4 to the power of x. There's nothing I can do. I've got something to the power of x. I can take the log of both sides, so I get the log of 5 is x times the log of 4. Solving for x, I get x is the log of 5 divided by the log of 4. Now the log of 5 and the log of 4 are numbers, right? And so to find the log of 5, for example, on your calculator, you have to first have 5 on the screen. And then you have to hit the LN button, which is on the left-hand side, fourth from the top, or fourth from the bottom, sorry. And so you've got an LN button. So you have to have whatever you want to take the log of on your screen. So 5, oops, not inverse, LN. And then just to be sure, it just gave me the answer, but sometimes it doesn't, so you have to hit the equal sign. And I get 1.6094379112. So if we have x as the log of 5 over the log of 4, we can write that. That's the same as 1.6094379112 over, and I'm going to store this so I don't have to type it all out. And 4, the log of that is 1.38629431. And then store that. Recall 1 divided by recall 2. I get 1.1609640447. Once you're used to taking the log, right, you could even do something like 5 log divided by 4 log, and it gives you the same answer, right? But you want to be able to check it, so just be careful. How about another example, example 128. Solve 3 plus y to the power of x equals 34 for x. 3 plus y to the power of x is simplified, so I'm just going to rewrite it here. 3 plus y to the power of x is 34. So all I can do is take the log of both sides to bring that x down in front. So I get x times the log of 3 plus y is 34. So we get x is 34 divided by the log of 3 plus y. Oh, what I forget? To take the log of both sides. Rookie mistake. Can't believe it. Now I can solve for x. X is the log of 34 divided by the log of 3 plus y. And then we can't simplify anymore. We could find the log of 34, but I don't think it's going to help that much because we still don't know the log of 3 plus y because we don't know why. We don't know why. We can't simplify. We can't simplify any further. Since we don't know why. Any questions? Then you have done your time. And that's all I've got for today. Thank goodness. Have a good long weekend, you guys. See you on Tuesday, I guess.